Okay, so if you look at question 2, so this is basically a question on testing your understanding of what is standard error. Okay, standard error is not the same as your standard deviation. All right, this one you have to be clear. Okay. The name sounds similar, but it's a totally different concept. All right. Okay. Okay. So you have counts, right? Okay. So you have some data here, which is let me see. There are 3 values here: 7. Oops. Okay, you have 7, 11, and 17. All right. So calculating the mean, this will be easy, right? Okay, you just basically add up these 3 numbers and then you divide by 3. Okay, so that will give you 35/3. Okay. Now, if you want to calculate the standard error of this is a standard error for the mean, right? Standard error for the mean is actually equal to the standard deviation of your this is your sample standard deviation, right? Over the square root of n. Okay, so in a sense, this standard error of the mean, this is a standard error of your sample mean. This is actually a sample mean, right? So when you have a sample mean, right, there is some kind of uncertainty related to this estimate, right? So this is your sample mean. Okay, your sample mean estimates the population mean, right? Right? It is an estimation, and since it is based on a sample, it has uncertainty. Okay, which means the next time you take another sample, right? Let's say you take a sample of size 3, you may not get 7, 11, or 17. Okay, you get maybe something like 5, 2, and then maybe 10 or something like that, right? So it'll be different. Okay, so every time you take, let's say suppose you redo the experiment, right? Redo experiment. You do a redo experiment, you may get something like 8, 12, 10. And then you do it another time, you might get something like 6, 10, and then 10, right? And so on and so forth, right? Maybe 12, 8, 6, right? So every time you redo this, you're gonna get a different value, right? So the mean will be, the sample mean will be, this will be 30/3, this will be 26/3, this will be 26/3, and so on, right? So it will fluctuate, right? Okay, so it will kind of like fluctuate around some. So the sample mean values will fluctuate around some range, all right? But they will be centered at some point here, right? So this point will be your population mean, okay? If you have randomization, right? So that they will be centered around the population mean, but they will have some fluctuation, okay? So this fluctuation here is captured by the standard error quantity, all right? So as you can see, if your sample size is large, right, it is a function of n, okay? So it's divided by square root of n. So if your square root of n is large, so if your n is large, right? If your n is large, then your standard error will go down, right, to 0. Okay, when this thing is large, because when your n is large, there is for example, if you take a large sample size, right, you keep on adding things, so this will be some large n, right? If this is the case, then your sample mean fluctuation will be very small, okay? Because you use more data, so the uncertainty is less, right? So the fluctuation will be small, and then it will be reflected as a drop in standard error, okay? If you take extremely large sample size, of course, you almost will have no fluctuation, okay? So that's the idea, right? So here is an example to help you do the calculation, right? Okay, let me see. So you are asked to find the standard error, okay? I should be sharing the whiteboard, okay, right. Okay, so first you calculate the standard deviation, all right? So the standard deviation in this case here, the sample standard deviation, right, is equal to, you take each value, right, 7, subtract the mean, right? Then you square it, and then you do for the rest, okay? Right, so these are your three quantities, okay? And then you divide by n less than 1, which is 2, okay? So that will be your standard deviation, sample standard deviation, okay? So your standard error will be this whole thing here, divide by square root of the sample size 3, okay? So the standard deviation, so I forgot to take the square root, okay? Right? So then you have some value here. Okay, is that clear? Right, so I'm going to clear the board for the next part. Well, maybe not. Let's see. Okay, in the next question, you're asked to find the sample size that you need to achieve a kind of a sample size that you need to take to achieve a standard error that is at most 1, all right? Okay, so let's look at that. Right, okay, so you have, so your standard error for the next study, right? So it's given by the standard deviation over square root of n, okay? So again, this n star, right, is the sample size for next study, okay? So usually in order to do some kind of large scale study, you might actually need to do some pilot study, right? The pilot study will actually help you discover something about the variability in your response variable, okay? So this one SD comes from here, okay? Comes from the current one, right? And you want to find, you want to basically prevent this from going above 1, okay? This is what you want, right? You want the SE, which is given by this expression, to be at most 1, right? So then basically you just rearrange and you will get your n star will be greater than or equals to SD squared, okay? So then you can, right? So then you take the take integer n that is closest to SD square and larger than it. Okay, so for example, you have, so let's say if your n star is 12.2, then you will take n to be 12, right? Okay, so it's basically just a conceptual question, right? With some very simple algebra. Okay. Right. Okay. Is this clear? Right. Okay. That's good. So I'll move on to question 4. Right. Okay. Question 4. In the university, the time that science students spend studying per week has a right-skewed distribution with mean 8.4 hours and a standard deviation of 2.7 hours, right? Then you get a sample, random sample of 45 science students, okay, and you're asked to find some probabilities, okay? So let me clear this. Okay, so you, in this case, let's say your X is the time spent studying, right? For science students, okay? So the mean of your X, this is the population mean, right? Is given by 8.4 and your standard deviation is 2.7, right? It's skewed to the right, right? So basically it means this is your time, right? That means something like this. Okay, there's a right tail that is long, right? So mostly people study around 8.4, right? This is the spread, but so a very minority of people, they, for whatever reason, they spend a lot of time studying. Okay, right? So that's the situation, right? And you take a random sample of 45 students, okay? You want to find the sample mean, right? So you take a sample of 45, then of course you will have 45 values, right? Which you can write as x1 until x45. So for example, one of them will be, maybe you'll get 8. The next one maybe 2.1. The next one maybe 3.4. And so on, right? And maybe the next one is 0.1. Okay, so you get a whole bunch of this, and you can find an average for them, right? Okay. Now the question is asking, before you even calculate this, right? What's the chance that your sample mean, right, is lying between 8 and 9? Okay. Before you even make the calculation, right? Okay. So what's the chance that you will get between 8 and 9? So this one, you will apply the central limit theorem, okay? Because basically you are interested in the distribution, in the sampling distribution, right? You want to find the distribution of the sample mean. So it doesn't matter whether your X is skewed, because the central limit theorem guarantees that the distribution of your sample mean is when the sample size is sufficiently large, right? It will be converging to the normal distribution, with the mean of x itself, and the variance is the variance of x but divided by n. Okay. So this is the central limit theorem result, right? So basically, you know that when your n is sufficiently large, your x bar will behave in terms of distribution like a normal distribution. Okay. So basically, then this n here is suppose is sufficiently large, right? So you could just subtract the mean and divide by the 2.7. Okay, then divide by square root of 45, right? This, okay, this whole thing you take the square root. Okay. So then you do the same on the right hand side. Okay. 2.7 over square root of 45. 9 minus 8.4 over this. Okay, so basically then this is actually just standard normal, right? Okay, this is just z. Okay, so basically then this becomes z is lying between two values here, right? Okay, so these two values you can calculate them yourself, and basically then you just need to check the statistical table, right? So this is maybe something like star here, and this is maybe your dot here. So basically you want this area under the curve, and that one you can use the statistical tables to help you. Okay, so that's the first part. The second part is less than 7.6 or more than 9.2. Okay, so the first thing is to note that x bar is less than 7.6 or x bar is more than 9.2, right? Okay. The first thing is to note that these two are events, right? This is one event, and this is another event. Okay. So these two events are mutually exclusive. Okay. Which means if the sample mean is below 7.6, it can't be above 9.2, right? And vice versa. Okay. So that means you have an OR here. So since they are mutually exclusive, this OR will you can basically this just simply means that you add up both of them, right? X bar less than 7.6 plus x bar more than 9.2. Okay, so the rest you just do the normalization, and then you separately calculate these two things, and then you just add up. Okay, right? Is this clear to you? Okay. And then what was the last question? Question 5. Okay. Okay, I think question 5 is also kind of like similar. So I'll just quickly go through that. Let me clear the drawings. Okay. So you have some kind of a product like a light bulb, and you want to, they are known to have a shelf lifetime, what do you call that? Shelf life, right? Of average life of 750 hours. That means they can continuously go 750 hours before they burn out. Okay, so then let's say your X is the life of life bulbs, okay? And I know that sigma x is 55. And I know that mu x is 750, okay? This is a given, right? Okay, so using the central limit theorem, find the probability that the sample mean of the lifetime of 100 such bulbs, right? So you take 100, so it's like this. So the lifetime will probably be something like this. Okay, most of the bulbs will be around the mu 750. Then the rest will be, some of them will be exceptional, but some of them will be a bit less. So those the distribution of the life will be something like this. All right. Then you take a sample of 100, which means let's say you randomly pick, right? If you randomly pick, you will pick something like this, maybe. You tend to get a lot of things around the mean, okay, with a bit from the tails, right? So after that, you calculate the sample mean, right? Okay. So every time you do this, it will be different, right? So you want to have some idea about what's the chance of your sample mean falling between certain intervals. So for example, here you want to find what's the chance that my sample mean will be more than 735. So again, this by application of the CLT, right? Central limit theorem, you subtract the mean, which is 750, and divide by the standard deviation over square root of n, right? So you do the same on the right-hand side, okay? 55 over square root of 100, okay? So this part is your z, right? And this obviously is a negative quantity. So basically you just check the statistical table. So this guy here is basically some star here, okay? So I just want to find the area under this curve, right? Okay, so you can find this easily, right? So this will basically be 1 subtract P of something. So this star is a negative value, okay? So this is easy to find. And then between 730 and 740, that will be basically the same type of question. So you want to find x bar between 730 and 740, right? So again, you do the same thing, right? Over 55 square root of 100 and so on, right? Okay, so basically this just gives you some 2 intervals, right? And you just want to count that, right? So that's why in your previous tutorials, you were given some exercises on calculating normal probabilities, right? For all sorts of situations. So that actually helps, okay? So make sure you know how to find that with the help of a sketch, okay? I need to keep emphasizing this. Use the sketch to help you determine where you should compute the area under the curve so that you don't make a mistake, all right? Students usually like to just play around with manipulating with this inequalities, and then they think they know some rules, and then they flip here, flip there. The situation is that a lot of times they just flip up, right? They just make a mistake. Okay, we see this very often every year in exam papers, right? You give some problems like this, and then students they do, but they never show the sketch, right? I don't know whether they know it or it's too easy, but then you see that they make some very careless mistakes, and that's a pity, right? because you won't make a mistake if you use a sketch to help you, right? So please make it a habit, right? Use a sketch to make sure that you know precisely where you are integrating the curve. Okay. Right, then the next one, within, let's see. So you want to find it within (15 hours of the population mean, okay? Within 15 hours, right? So within 15 hours of the population mean, that would be the following. To find X bar is within 15 hours, right, from the population mean. So the population mean is 750. So it'll be plus minus, right? Okay, so basically this is 735 and this is 765, okay? Right, so roughly, right, you could actually note that this will be actually quite high, because this part here is about 5.5, right? So here this is about close to 3 times of the standard error. So by the empirical rule, this will be about 3 times of standard error. Okay. So this will be close to 99.7%. Okay. All right. So basically, you can just translate the question to this form, and then you can just solve as you did for part 2. All right. So all right. So the meeting is coming to an end, less than 1 minute. So we'll stop